like you full screen to the right.
Okay, well, let's stick with. I remember this happened last time, so
Okay, yeah.
let's just stick with this. So
All right,
I think we are here, right?
here. Yep.
Cool.
So yeah, so anyways, this is first run flash attention, which I'm happy to present because this is, I think, one of my favorite algorithms just in all of machine learning because I think it's a very beautiful combination of concepts, and I was really, it was what enamored me with sort of more systems level stuff. So I really love that I get to present it to you. So anyways, next slide. So motivating flash attention is that long context is really, really, really hard with quadratic attention, right? So at a certain point, it just expands, and you have this, there's so many attention heads, so many decoder blocks that if each head has to have this big matrix of attention scores stored in GPU memory, the overhead from one just trying to store all these and then actually having to load them and compute off of them gets insane. As to where past a certain point, it's basically just impossible. And you will just run out of device memory, or you have to do some very, very brutal offloading step. And it's just really, really painful. But next slide. So the key idea in flash attention is to be I/O aware, right? So as we sort of went over last week, one of the biggest bottlenecks in GPU computing is the fact that you have this pretty big device memory, but it's really, compared to how fast the compute cores are, it's really slow to get things actually on chip and, things running. So you want to ideally do as few loads as possible and get as much work done per byte you have to load off of GPU memory. So this is the, I think, H100 numbers here, where you see about 3 terabytes per second up, and then but a whole almost 1,000 teraflops per second of tensor core compute, which means you really need to be judicious with your loads and make sure that if you load something, you don't want to be doing, saves that are unnecessary. So it sort of loops back to this idea of arithmetic intensity, where the whole game is, reduce the number of memory accesses per floating point operation. And, crank that arithmetic intensity up until you're hopefully compute bound. And then once you're compute bound, there's like not very much you can do. You just have to get more GPUs or something. Next slide, please. So this is the standard attention formulation, which I assume everyone is very, very familiar with, but I feel like everyone starts every presentation with this, so we're going to go over it. But the key thing to look at here is that this is thinking about what the actual device is doing. So you're loading blocks of these, your query and key matrices into compute chips and off of HBM, and then you're doing this softmax, and then you're writing it back, and then you're reading it again, and then you're doing the value matrix multiplication. And the key thing to think about here immediately is, oftentimes we think of, you just do a torch matmul and we magically get everything back. But actually on the GPU side, the GPU has to tile things out. You can't fit that much into SRAM, so it has to figure out how to decompose this matmul into many smaller operations that it can load into SRAM, and then that gets decomposed into smaller operations that it can load into tensor cores. And you have to have a little bit more of a systems mindset when you're thinking about actually what's going on at that level. All right, next slide, thanks. So this is the sort of the high level overview of what the attention is on chip, right? So you have this queries and keys, and then you're loading them in, and then you're softmaxing over rows, right? But The problem, at least naively, is that Softmax requires this entire row to be in memory, and not even on memory, but you need it to actually be on chip, right? Because you need to do this accumulation. And this is really a drag because we want really long contexts. We want to be able to do, 32K context. We want to be able to do 64K context. And that means this n by n matrix gets very, very large. So ideally, we would like to have a way as to where we never really have to represent this n by n matrix, at least not explicitly, not in device memory, maybe only, transiently individual blocks of it on chip. So the game plan here is we want to figure out how to do this computation here without ever having to put these whole huge S and P matrices into our device memory. So the key concept behind that is next slide, which is tiling, this is sort of what matrix multiplies are under the hood on GPUs. It's not just taking some huge matrices and somehow they magically get thrown together. It's GPUs love many, many, many small tile-wise accumulations. So if you see on the right, the way that matmulls actually happen is you load some tiles into SRAM, and then once they're in SRAM, you compute even more small matrix multiply accumulates to solve the actual, and then once all these things get accumulated, you've done your matrix multiply. So the key things here are things in SRAM are a lot faster than device memory, and also when you actually get things into SRAM, what is actually doing all this compute is your tensor cores. And your tensor cores are basically little specialized device memory that their whole thing is small matrix multiplies. They really like, 16 by 16 matrix multiplies, and they are not very happy to do much else for you. Okay, next slide, thanks. So let's talk a little bit more about tensor cores, because in my mind, tensor cores are at the heart of tiling. And these are, again, very specialized hardware, and they are incredibly important for throughput. Where if you look at the flops here, these are numbers for an H100, basically all your actual flops are coming from tensor cores. Literally everything else is like 5% of what your tensor cores can provide. So if you're doing these dense operations, these dense malls, and you're not using tensor cores, you've lost from a performance standpoint, right? There's 0% chance that you will achieve any real performance. So we really need to have this tiling in all our matmulls because that is how you feed tensor cores. So that's why if you sort of look at this graphic here, when you think of, or at least when I think of matmulls, I actually think of the picture on the right where you have these row column dot products. But you can't do that on tensor cores because tensor cores want chunks of memory because they want to do 16 by 16, accumulates to solve the matmul problem, which is why, when we're going through this paper and when Daniel's going through his implementation later, you're going to see that everything is done as a block and there are no long skinny things, that everything is done start to finish because you want to get that tensor core performance. So really, for me, flash attention is all about how do we maintain our tensor core performance while, dealing with this annoying softmax. All right, next slide. So this is to further motivate tensor cores. I'm a big tensor core fan, so if that's not obvious already. This is a picture of an H100 SM, or streaming multiprocessor, which is where all the actual compute happens, basically. But if you look here, the one thing I will motivate is the tensor core seems to take up a lot of chip real estate. So if you're not using those huge tensor cores, which is, very specialized hardware to do this kind of stuff, you're really losing out, right? You spent tens of thousands of dollars on this single H100, and look how much of that chip real estate you're not using because you've not effectively tiled things out. You're not using tensor cores. So it's really all going to be about that. Next page, please. All right. So imagine for a moment that you didn't need to do softmax. Softmax is going to be an annoying thing for attention. It requires this, we need this whole row. Then it's actually very easy to do this whole attention computation, right? Because you would just, compute a tile in SRAM and then do one more matmul with that tile with a value matrix, and then you get your output, right? So it's very easy to do this if you don't care about any of those activation stuff. So the next one's a couple tiling slides, so you can go through that pretty quick. Yeah. So you just accumulate all of those, and then you're done. But tiling is how. So okay. The tiling with softmax is a bit of a tricky thing, though, because again, naively you would think, okay, we need this whole row to compute the softmax. So maybe this would be my natural first attempt is, maybe we just try to compute this whole row in shared memory, right? So if you go through here, yes, you can. You just compute this whole row and take the softmax of it, multiply it with the value matrix. But this is, again, would never ever work because this is going to require way too much shared memory to do these tiles. And then you're going to immediately explode. You're going to get that notorious CUDA right? So you really have to think, how do we solve this? So the next slide, can you go to the next slide? The next thing you could think is, why don't we make this very skinny? And the answer is, well, then we can't use tensor cores, and suddenly we've lost again, right? Because, maybe you've solved this loading into shared memory problem, but if you're not doing your matmuls with tensor cores, you've lost 95% of your performance. You've solved a small problem and introduced a much bigger problem, right? So next slide, please. So here is the next thing that's really important is how do we deal with this softmax that is preventing this exponential, that is preventing us from doing this tiling that we really want to get our tensor core performance. So the first thing, when you look at the softmax formula, you look at that sum and you think, well, maybe this is impossible. But then you look at it again and you're like, oh, these are actually the nicest functions that we have. We got that lovely e to the x, and we got just a nice splittable sum on the bottom. So maybe we can play around with this and figure out a way to do this that doesn't require us having to do all these things at once, and maybe we can combine them. So the first thing to note is, why do we have this max term with the EDX? And what it actually is its numerical stability, right? So if you think of attention scores through training, they can get pretty large, and if they get to a point where e to the x gets also very large, so if you ever actually try to materialize e to the x on hardware, and it's x is big enough to go out of the dynamic range of whatever data type you're using, you're in for a very, very bad time. This is when NAND starts showing up and things start exploding. And then you wake up the next morning and your training run has gone to hell and you're crying. At least that's my experience of it. But so what people normally do is they subtract the max of the vector from it. So what the point of that is if you subtract the max of the vector, it's not actually changing the value of this, but it is changing the fact that you can now always have e to the x minus max of x on hardware, because that is at most 1, because it's at most e to the 0. So therefore you deal with a lot of these issues. But what is actually another thing that's important to note is max of x is chosen for stability reasons, as in this is a value you can always pick that will show that this will never overflow. But it's not actually special. You could pick C, you could pick B, you could pick 42, and you can sort of swap them in and out by the fact that you can factor them out and then add a new one in. Right, next slide. So what I'm going to have to now convince you of is we can take two separate Softmax tiles. So think of these are the tiles we had to load into SRAM, and we've done them independently. We've done all this Softmax and stuff. And now we need but eventually we're going to need the whole tiling across the entire key values, right? So we have to combine two separate tiles into one bigger tile. So the key things to look at these formulas is, well, the bottom is sort of just a denominator value, right? It's something that we divide everything by, and it's going to be the same always across the whole vector. So perhaps we can always multiply to get that out. And we've already explained that the numerator is very swappable. So that sort of motivates that this is probably not actually as hard as we initially thought. So anyways, next slide. Okay. So the key thing is when we're doing softmax, there are some key values we have to keep track of, basically, in order to be able to combine these later. So the key values are the maximum value, which is what you were using for numerical stability. And you want to keep track of the denominator, basically because we want to be able to remove the denominator later and add a new denominator. All right, next slide, please. So as we compute softmax, we're basically going to need to swap these numerator terms and the denominator term. So the key value here is that when you're doing e minus x, you can, when you're multiplying in e, it gets rid of the old one, and then you're subtracting the new value. So max of x was the old value in the numerator, and now you can get rid of that. And then you can combine them with when you've added in the new scaling value. So it's basically very simple algebra. And then once you combine these two sums in the bottom line, you get the new denominator across this whole double vector, which is something that we can then use to combine tiles, right? So next one, please. So this is sort of putting it all together. So we have one tile, softmax x, and then you can take that and subtract change. I say subtract very loosely. You can change the scaling term of the numerator by just adding, multiplying with this max minus max xy, which is max across the whole vector. And the key thing you have to note here is, why do we need to do these in one multiplication? And that's like, why can't we just multiply by max of x first and then multiply by e to the negative max? And it again comes back to the fact that you need to do these at once, all the time, everywhere, because you can never materialize e to the x on hardware, because if at any point you do, it'll probably something somewhere may overflow. So you always need to be doing this rescaling step as to where you are both, removing the old scaling value and adding the new scaling value at the same time. All right. And then once we do that, you can just swap the denominators, right? Because you have the old denominator, which is one of the things we keep track of. And from the last slide, you can see how we can calculate the new denominator. So just, multiply in the old one and divide by the new one, and it's done. All right, next slide, please. So this is sort of all the steps we have to put together. It's basically the entire algorithm. But what's actually very beautiful about this, in my opinion, is the fact that this is actually coming very, very close to the pure idealized tiling case that we talked about earlier with tensor cores, where you could almost completely ignore the softmax and just worry about your matrix tiling. And then, but here you still need to do, a couple adjustment steps, most notably the adjustment step at the end where you're doing this rescaling of both the denominator and the top numerator value. And you have to now do your softmaxes tile-wise. But that's actually very fast because we're already going to have this tile in SRAM when we do for our tensor cores to do this, query key computation. And then you just sort of throw in a softmax computation. It's already there. It's basically free. And then you just, you can do this value computation, and then you can throw it back in with the rescaling. Notably, again, because we're computing these tile-wise, we're doing tile-wise accumulates here. So you're not actually just computing the whole value with one single pass. What you need to do, just like with all matrix multiplies, is you're accumulating the value into the O vector, or the O tensor at the end. Next slide, please. So this is putting it all together. This is the actual algorithm from the paper. And the key sort of things that I want to go over here is, we now know why are we motivated into chunking these into blocks. So we can fit these blocks into memory or SRAM, and then we can do these tensor core computations, right? So the key thing here is you choose your SRAM. Based on your SRAM sizes, you choose your block sizes so that everything fits onto SRAM, right? So this is why you can sort of see, why is BR the minimum of M divided by 4D? And it's, if you do the math out, it's so that all these tiles and their resulting intermediate products can fit into, GPU memory, or always SRAM, fast GPU memory. And then once you have that, you can just do this very normal tiling computation, which is, line 9. And then you take these scaling values, which we talked about earlier, right? So M is our numerator rescaling value, and we're going to need to cache that for later. And then L is our running denominator. And then once you add those in with chip, with your chip, I don't know why I said chip. But once you multiply those in with your final output matrix, you're good to go, right? So, and there's a quick note as to why you can do this rescaling step right at the end. It's because all this is wonderfully linear, right? So you have this value that is technically a rescaling step that happens in the middle of the softmax, but you can multiply it in right at the end because these are all linear equations, right? So if you're doing something quadratic in there, then you would have to scale earlier. But because these are all linear equations, you can just do this fast little adjustment step on the final tile before saving it back to main memory. And that's very quick then. Next slide, please. So these are the results. They actually I was very impressed with these. These are, considering you had basically half of NVIDIA trying to, implement Megatron LM, and then they cooked them pretty bad. At least with on this GPT-2's training. So the other thing that's really interesting to note here is that there's like a crossover point between where this is the ideal way to compute this and where you would just want to use normal eager attention actually does, outperform for very short sequence lengths, right? So for very short sequence lengths where the quadratic cost of memory of pulling things in and out of HRAM is not so high, not so bad, then you don't have as big an issue. So you can see that there's some crossover point of about, somewhere between 500 and 1,000 in context length where this suddenly becomes faster to actually do these recomputation steps, and instead of this, just holding these in memory forever and then loading them from back and forth. But the other thing that's very interesting is even if you're not worried about time, you should be worried about memory, right? Because memory is magical, because memory allows you to do long sequence tasks. But you can see that the PyTorch implementation, even for very, very, very small sequence lengths, just balloons in memory, right? This is that quadratic memory requirement. And if you have to hold these, n by n matrices in memory for your entire forward pass to use in your backwards pass, life gets very troublesome very quickly, right? So you see this 20x difference even for, relatively mid-sized context lengths. All right. Next slide. All right. So a quick note on what flash attention. So now I hope that you have some sort of idea of what flash attention 1 does. But why did they have to make 2 and then a third sequel is an interesting question, right? So the second iteration was built for A100s, and that was to remove a lot of redundant scaling operations, right? So you have here that in our implementation we've seen so far, oftentimes we're swapping out the numerator and the denominator all the time, many, many, many times. And it turns out that tensor cores are so fast that even these, relatively cheap pointwise operations on something that's already in SRAM becomes slow by comparison, or at least it's adding non-negligible overhead. And for that reason, in Flash Attention 2, they swapped the loop order and they've sort of factor things out as to where in the outer loop you can have this rescaling operation, so you only have to do it a fraction of the number of times. You have to do it instead of a quadratic number of times, only a linear number of times. And they also introduced parallelization over Q, which is a huge number of, for very long context operations, you tend to have very low batch sizes. So if you parallelize over Q, you can then allows you to have better residency on hardware, where you have more things running on your SMs at any point in time, which is just good. So they found that achieved about 73% of the max theoretical flops on an A100, which is a pretty impressive result to go from something that was like strongly memory bound to getting a solid chunk of what would be the theoretical very, very max peak, right? And then Flash Attention 3 is sort of where my knowledge caps out, where this is now becomes a game of using very fancy features of the H100, specifically their asynchronous memory loading operations and their asynchronous tensor core dispatches really becomes key to the performance there. But really what you can think of is if you're using an A100, you're fine with Flash Attention 2. If you're using an H100, it's probably good to update to Flash Attention 3. All right, next slide, please. Oh, I think this is about this is what I was going to have for discussion topics, but I don't know if we can really do a discussion with the current format. Do you want to swap over presenters now, Daniel? Or I guess you're already presenting, so you can.
Yeah. Sweet. Okay. All right. So now we'll just go over a quick. I won't spend too much time on this, but this is a Triton kernel implemented for the basic flash attention algorithm. To be clear, this is the point of the way I've implemented this is not to be like the most highly optimized implementation you're going to see. It's far from that. You can find like in the official Triton docs, they have like a very highly optimized implementation. But the problem with that I found is it stops like the structure of the code and kind of stops resembling the actual mathematical formulation of the algorithm that we just saw, and it kind of becomes hard to parse, especially if you're just learning this like me. So I found it helpful to just kind of do a simpler implementation that kind of more closely resembles the actual math. And yeah, so basically here what we're doing is just implementing a simple like torch autograd function, which will allow us to define our forward and in particular our backward pass manually, and I'll just rely on AutoGrad machinery, which I have not done yet. I've only done the forward pass, but that's kind of the key part that we talked about in the slides, so I'll just cover that. Yeah, so the first thing to note here is that we are going to define our grid, how we're going to parallelize this computation on our hardware. And they kind of, if everybody here who was in the last session where I talked a little bit about CUDA, this is going to require a little bit of a shift in our mental model, because rather than basically in CUDA we're only worried about like one thread in our actual CUDA kernel itself after we define our grid. Here, we're going to be defining these thread blocks, but then our actual kernel itself will be operating on the block level. So there's just a little bit shift in our thinking that needs to happen. So I want to say that up front. So now how we're going to define our grid is going to be first, along the first dimension here, we are dividing our sequence length by our block size q. So essentially, each element in our sequence will be associated with one query vector, and we are chunking up these query vectors into blocks of block size q, right? And then we are also, along our next dimension here in our grid, we are going to have batch size times number of elements along that dimension. So that's going to be the size of the grid along the second dimension. And so basically what we're going to have here is like a 2D grid of size. We're parallelizing across a total size. The total size of the grid will be a number of thread blocks, which is equal to our q blocks, which is our sequence length divided by our q block size, times our total batch size, times our number of attention heads. So we're parallelizing both across our queries, across each index across our batch dimension, so basically across each example, and then across each attention head. Okay, so this is the grid that we've defined. Now we can actually use this kind of Triton syntax here to actually launch our kernel, and you can see, just for a frame of reference, we have these q, k, and v are projections. They've already gone through our linear layers, so we're of size batch size by num heads by sequence length by head dimension. So they've been projected from the embedding dimension to the head dimension already, and now we are just launching our flash attention kernel. And here, our softmax scale, that's like our 1 over square root of dk, you'll see, and commonly that's the scale we use. And then we also need to pass in our strides. This is important because here, these are torch tensors, right? This is coming from like a PyTorch. We're dropping in to the Triton, like to the kernel layer, where when we load these later, these are just going to be blocks of memory, right? Which is basically an array. And that means that we actually need to know our strides in order to understand how to index. Like if we want to get to a certain index in the batch and a certain attention head, and then we need to know the strides in order to figure out how to index into this array, basically. So we pass in our strides, and then these are just other hyperparameters like batch size, sequence length, etc. And then the block sizes that we want to use, which I've manually just hard-coded here, but you would like auto-tune these. So then let's jump into the actual kernel itself, where things get interesting now that we have that context of how we're like parallelizing this and such. So first thing we're going to do, similar to CUDA, we're going to figure out which thread block we are. So we're going to ask Triton, what's my index, across the first dimension, our first axis rather, axis 0, and then our index across the axis 1. And so the way we defined our grid up there, this is going to be our query block index, and this is going to be the product of the batch that we're operating, or the index in the batch dimension, and then the index in the head dimension, and we multiplied those. So that's going to tell us basically the coordinates, like which thread block we are. Now we can decompose that batch times head index to separate those out, right? So now we know exactly which index in the batch dimension that we are responsible for, as well as which attention head for that batch, right? Now this is where we start actually having to deal with memory and doing pointer arithmetic manually. So this is important. We now need to go from our base Q pointer, right, to our offset where this batch and head index actually begin. So we need to use our strides to calculate that, right? So we go from the base pointer and use this offset to then go to where this particular subtensor that we're responsible for in this thread block is located in memory, right? So we are adding. So now we're going to use this abstraction to basically called make block pointer. It's a Triton function that will give us basically, in this case, a 2D block of pointers basically for elements in memory that we are going to be wanting to pull in for this Q block that we're going to be using in our flash attention algorithm here. And so the base pointer is going to be the beginning of the whole Q matrix plus the offsets that we calculated here for this specific batch and head. So I've added the kind of torch indexing equivalent here because I think that makes it easier to understand. So this is where we're going here, right? And we're saying this shape now that we've done these two indexes, this batch index, this head index, this shape that we are now looking at is going to be sequence length by head dim, right? Because we're grabbing, it's like grabbing everything is basically these two lines is what we're saying, right? So that's what this is doing. And it needs the strides to know how to do this, right? Now we're saying, okay, we have this like parent subtensor, so to speak. Now we actually need our Q block, right? The whole point is to start like doing this tiling algorithm. So basically what we want is to grab a subset. Our Q block is going to consist of a subset along the sequence dimension, right? Because each element in the sequence is going to have an associated Q vector associated with it. We want to grab a subset of those Q vectors of block size Q, that's how many we want, and we want the full head dimension for each of them. So we're not chunking across the head dimension, we're grabbing the full head dimension for each Q, right? And then we need our offsets in order for it to know how to get this like this block of memory for us, basically. So we tell it which query block index we are and how many elements per query block, and then on the height dimension, we just stay at 0 offset, right? Because we want we want to start at the beginning of the head dimension. We don't want to jump. We don't want to do this indexing here where we're jumping to some specific query block index, right? So that's like the final shape we're going to end up with here. Don't worry about this line. It's just like for Triton compiler optimization. I've actually not found like a good explanation of what this does, but you have to put it, and if it doesn't actually affect the output values, like you can swap these around, nothing changes. It's just it changes how it will be compiled, apparently. So would love to learn more about that if anybody can share after this. And then for K, V, and O, we just do similar logic. One just difference here is that it's important to note, K needs to be transposed with respect to Q. So we need to reverse our shapes, our strides, and our block shape, right? And then for our offsets, remember for each Q in this algorithm, we are going to be going and we're going to be iterating through each K block. So for one Q block, we're going to iterate through each K block, and so we don't actually want to start like at this one where we started at some Q block index. We're starting at 0. We're starting at the beginning. So we offset. We just start at 0. Cool. So now we've set up our we've done some pointer arithmetic here to get our Q, V, K, and O block pointers. O is our output, just as a reminder, where we're going to be writing to. And now we can start kind of cross-referencing with our actual algorithm. So I'm going to pull this up. Oh man, wait, I can't, you guys can't see the algorithm, can you? Okay, well, I was going to cross-reference with the paper, but it's going to be annoying to try to reshare everything. So yeah, let's just stick with it. So hopefully this notation is helpful. So in the algorithm, we had this like m sub I value, which was the max max score that we've seen in our QK matmul so far as we go through this tiling algorithm, right? We have this like running max, right, that we keep updating through each iteration of the inner loop. Let me just see really quick. I just want to see if I can share, because this is going to be, I would really love to show the paper. Can I just show my whole window? Screens? Here we go. Wait. Whoops. Screens. Screen 2. Okay, tell me, can people see the code? Can somebody pipe up? Hello?
I can see the code and your Discord.
Okay, you can see this now.
Yes.
Too.
Yeah. Okay, beautiful.
Sweet. Okay. So yeah, so first thing, as you see here, and by the way, this is the flash attention 2 forward pass. Then discussed a couple of the differences, like we do Q in the outer loop now, so that's why we're parallelizing across Q in this implementation, right? So all of these instances, all these iterations for Q across Q blocks are parallelized, right? So in our implementation, we're going to see only one loop, and that's this inner loop here, okay? So at the beginning, before this inner loop, we need to do a few things. We need to initialize O, we need to initialize our running denominator we're going to be calculating, and then we need to initialize our running max MI. So here, that's what I'm doing here. I have my MI, which I've called global QK max, and then our L sub I, which is our global softmax denominator that we're going to be, it's like our running denominator we're calculating. Our accumulator for the O block, right, we're initializing that as well, as you can see here. And then now we can start actually, it says load Q from HBM into SRAM. So that's what we do here. We are loading, using our Q block pointer, we are loading it into SRAM. And now we have this shape of block size Q by the head dimension, right? And so now what we can do is we can enter our inner loop officially, and we're going to go through the key blocks and value blocks, but one at a time. So what we're going to do is start at 0, right? We need to go through all of them. And just to clarify, this is causal attention that I've implemented here. So we're stopping at the diagonal, essentially, where the key indexes would start to be higher than the query indexes, and thus are not relevant to causal attention. We only want the queries to reference keys that are quote-unquote in the past, right, that it can see. So that's why we're stopping early here. And we're going to be going block size KV at a time, right? So now we can first set up our causal mask, which is going to be done by referencing these offsets that I've set up, right? So we need to figure out what our offsets for this particular Q block. So we need to jump to this Q block index multiplied by our block size Q, right? That'll jump to the first offset of this Q block plus this A range of block size Q. So what this actually holds is, you can think of it like a list, basically, of offsets, right? And then this also, KV, is a list of offsets. And then on each iteration, on each key block that we are iterating through, we can use these to create this 2D causal mask, right? Which is just doing, this is creating a column vector with this syntax, this is creating a row vector with this syntax, and we're jumping to, we're adding this, 0 through 15, say, to the starting KV index of this KV block that we're at, and using this to compare these offsets and use the broadcasting mechanism to basically just create a causal mask. Okay, so now we have our causal mask. We can do the next step of the algorithm. So looking here, it says load K and V, the K and V blocks rather, from HBM onto SRAM. Cool. So we load from HBM onto SRAM. Done. All right, now we can actually do our first mapmul here for our QK block, which the notation they use is S sub I here. So we do our mapmul with Q and K transposed, and then we multiply by our scale, which is usually like 1 over square root dk, and then we apply our causal mask, right? And now we go to the next step, which is computing. This is where we get to the the kind of corrective factor that Ben was referencing in his presentation. So basically, we're now computing M sub I here, right? Where we are looking at, first we need to find the local max for each row, right? So that's what I'm doing here. So this row max notation here for the scores, that's what we're doing. We're getting the max for the scores we've calculated across each query, right? Each query is going to have its own maximum that we've seen, right? And then we are going to compare. We are going to compute our global max, or sorry, our corrective factor, right? And so this is a very important. It's going to be used a couple times here. Here you can see how we're subtracting the previous global max minus the new local max that we've seen, right? So here we see that. That is why we are storing that result in a variable here. So we are doing the previously seen global max of the scores minus the local scores that we see in this particular iteration, and then exponentiating to achieve this e to the number, which is our corrective factor that we can multiply by later to correct our previously seen global softmax denominator, to adjust it based on the new max that we've seen. Since previously we might have been exponentiating subtracting a max on each iteration that was not actually the true global max for the row. And since we're tiling, on each tile we need to track what is the new global max and what was the previous one, so we know how much to adjust the previous global softmax denominator by. So let's keep going. So we have our local max, we have our corrective factor. So now we can compute our P block, which here you can see it is we're exponentiating our scores minus the local max. So this is for numerical stability, like Ben referenced. Take our scores, subtract the max, and then we exponentiate and we store it in this P block, right? So here's our P block. Now we do our row sum, which is going to be used in our denominator. So here, now we're computing L sub I. This is like kind of the important part, right? So this is our cumulative or like running denominator that we're calculating through this tiled algorithm, right? So this is the row sum part. We're row summing across the P block here, right? So that's what we're doing here. Now, to actually compute the new updated global softmax denominator, we multiply the corrective factor, right? So which is here, the e raised to the previous max minus the new max, which is our corrective factor, right? So this is our corrective factor minus our previous global softmax denominator plus our row sum. And if we look at our code, here we have our corrective factor times our previous global softmax denominator plus our row sums, right? So this line right here is implemented right here. Okay, hope that makes sense. Now we are ready to update our new global max, because previously I kept them separate because we needed to compute the difference between them to know our corrective factor, right? So I kept them separate, but now we're ready to update the global max. Now, if we move on to the next line, we're at the bottom of the for loop here. We now need to compute. We need to update our accumulated O. We need to accumulate the results in this O block that we are seeing. So what we're going to do is multiply our corrective factor again. So here's our corrective factor times, or in this case, they're doing a matmul, as Ben mentioned. They want everything to be a matmul if possible to achieve max flops utilization essentially. And so they're effectively applying this corrective factor to the previous output matrix, like the running output matrix output block that we've accumulated so far, applying the corrective factor to it, and then adding our new rho max times v, like this would be like our local O value, the softmax O, or the softmax S, right here, minus the M for numerical stability, that's what P is, times V. So this is like the standard attention stuff, right? So just that local sum, or that local matmul, and that's what we're doing here. So we have our previous O block, which is here, applying our corrective factor, and here I was naughty. I did not diagonalize this and make it a matmul, so we are not achieving. This is not the most optimized implementation, but it is accurate. I have like some unit tests down here, but basically we're applying the corrective factor to the previous O block, and then we are multiplying this we are adding this to the matmul of P and V. So this is this line. Corrective factor to the previous O plus P matmul V. Corrective factor times previous O, and then add P matmul V. Okay. Now, finally, we are ready to iterate to the next block of keys and values. And so we will just use this Triton function here, which advances the block pointers. And if you just remember the dimensions here, this is our for K block. This is a dimensions head by our K block size. So our sequence length. Sorry, and then so we iterate along the sequence dimension by block size KV. And then for V, this is not transposed with respect to Q, so this is our sequence dimension. We iterate by block size KV along the sequence dimension. And then we go back up here and we do the whole thing over again for the next block, and the next block, and the next block, right? And then now when we've gone through all of our K blocks, right, for the single Q block, right, this is one thread block, we're finally ready to use this running softmax score that we've been accumulating, right? So now we can do what Ben talked about, where we can finally normalize the values and apply our global softmax denominator to our output block, and then write our output block back to HBM, right? And so yes, that's the algorithm. Hopefully that made sense. If Triton's a bit tricky. For context, I've also been just learning Triton over the past week or week and a half, and started with simpler kernels, and if this is kind of the latest one that I've done. So somebody please let me know if something's wrong in here. But this simple unit test with just a reference implementation using a few torch primitives and then comparing it to my Triton implementation here, it passes with this torch all close here for this particular input size. One thing I noticed is that if I increase this to very large input sizes, this starts failing, and I believe this is just because of floating point divergence that occurs. I was asking around about what could cause this, and I think the most likely explanation is, for a given floating point element, when you do some multiplication or something, there's going to be very, very small divergence between floating point values when you're computing them in two different instances, right? But then if you're accumulating across thousands or millions of different elements and like reductions and operations like that, then they'll start to accumulate, and the final errors in the output might be, or differences rather, might be larger. But I believe the algorithm is correct because for a pretty, batch size 2, number of heads 2, sequence length 32, head dim 64, it matches the torch implementation. But yeah, that's all I had. Hopefully that helps make things more concrete for people. And with that, I'm going to hand the streaming and stage back to Ben, who has, I guess I can pull the slides actually again. Hold on.
Yeah. Does anyone have anything they want to chat about, or anything that was unclear, or want to come up on stage and discuss something? There's a raise hand button, I think.
I have like 2 dumb questions if nobody else does. All right, well, someone's typing, but I'm just going to ask a quick question. So we're subtracting by, one thing I was wondering, when we're subtracting by the max for numerical stability reasons, so like the max we're exponentiating to is like e to the 0, right? It'll be like 1. But if there's a very large range between the minimum and the maximum, I'm wondering if we could, instead of running into overflow issues, run into underflow. Is that even something that needs to be worried about in practice? Like if it becomes a hugely negative exponential, rather number we're exponentiating to?
It's a good question. In theory, right, it should be crushed down to 0, right? Mm-hmm. So, because, e to the, minus infinity goes to 0. So it should never actually become negative, right? It should always just become 0, and then it's like, oh, you skipped that entry, right?
I see. So it'll just basically become 0.
Yeah, which is, so it's sort of, because the idea is you're trying to, every value there should be between 0 and 1, basically, right? Because, so I think, I don't think it would happen in practice, because I think it would be very annoying if your hardware should hopefully be correct. Well, it depends on the implementation of, exponentiation, but you would hope that it's correct across, all valid BF16 values or whatever, right? That it's not underflowing. Whereas, of course, with overflow, the fact is, you dispatch some mathematical operation that is literally impossible for it to represent, right? Mm-hmm. So there's no way to fail out cleanly there.
All right, I guess that makes sense. Interesting. I have one more question if nobody else does. Oh, we can also talk about this, but yeah, I was actually wondering, one thing you said in the presentation on one of these slides. Yeah, here, could you go over what you meant again, like remove a lot of redundant scaling by swapping Q and K, like the order of the outer for loop and the inner loop?
I don't know. But it was, if you look through the implementation, right? Mm-hmm. Oh, I don't know. Now I did it. If you compare them side by side, mm-hmm. You can see that the denominator scaling is now on the outer loop. So can you bring up the flash attention 2 and flash attention 1 papers? You compare them. So if you look here, in this implementation here, the denominator rescaling and stuff it's in the inner for loop, right? Mm-hmm. So if you look at the other one, it's on the outer for loop, right?
Oh, got you. I see.
So that means you're doing it, instead of a quadratic number of times, a linear number of times, right?
Yeah. Okay, I see now.
So yeah, the motivation here is that you don't really you just need to put the final values in there, right? Mm-hmm. We don't really care about the intermediate denominators. We only really care about putting the final correct denominator in there. and you can do that right before you write back, O of I, but you actually have to switch the loop order as well, right? So if you go back to 2, now you have QI on the outside, and more importantly, you have OI on the outside, which means that when OI is getting written back, this is, the last time we'll ever really see it. So that means you can do this scaling right at the end, as opposed to having to load OI back in and rescale. So you can, by swapping the loop order, you can bring this rescaling step out of the, factor it out, and it'll decrease overhead, because you're doing a huge amount of redundant rescaling in the other version, actually.
That makes sense. Yeah, and I just noticed here in Flash Attention 1, they're loading OI from HBM onto SRAM on every iteration of the for loop, and then writing it back out to HBM. So they're like moving it back and forth, from HBM to SRAM back over and over again. Whereas here, we just have this one.
I guess you're getting rid of a write as well, right? Because you're gonna have to do the loads anyways, because you need, 2 of the tiles need to be. You always need to be loading 2 and 2, whichever loop order you need to do, but you don't necessarily need to be writing that much either.
Right, but wait, no, so we need to hold on, because here, when you say 2 and 2, which blocks are you referring to? Are you talking about Q and then the K, each K block, or?
Yeah, so you have to be, so in the every tile throughout these run loops you get the same amount of loads, right? Because it does, no matter which way you tile, the same things need to be loaded eventually.
Is it though? Because I thought here it seems like the one thing that's different is we're still loading the same amount of Q's and K, like Q and K blocks, but the O of I we're loading from HBM onto SRAM like a quadratic number of times, right? And
but in the past iteration you were actually loading the internal loop a quadratic number of times, right? So here you're loading Q and K quadratic number of times in this implementation, which is Flash Attention 2, and the other one you're only loading K and V a linear number of times, right? So in Flash Attention 2, you're loading, but you can still say, and these are all roughly the same block size. So
it's really the right. It's really the right that we're saving here.
Yeah, basically. But you're getting rid of a right, right? So that's so it's sort of like you have 4 out of 5 instead of having to do all these 5 things. So I think a write and a read are relatively similar in I/O overhead. But yeah, this is doing a quadratic number of writes, and the other one's only doing a linear number of writes. So actually, no, so I'm stupid. So it's 4 out of 5, but quadratic instead of linear.
And then what about? Sorry. Go ahead.
No, you can go. You have a.
Yeah, this section. The outer loop over sequence length is embarrassingly parallel. So essentially, we can parallelize over Q blocks arbitrarily, but we need to schedule them on different dot blocks and not need to communicate with each other. Okay. We also parallelize on the batch dimension. Blah blah. Hold on. No, this is this. No. This is what I was talking about. Yeah, here. I feel like this is kind of important, right?
So this is the different tiling?
Yeah, so essentially I was trying to understand, it's basically making the assertion that you need to do actual synchronization to accumulate results in shared memory, like intermediate results in the old Flash Attention by parallelizing over Q and V rather than, K and V over instead of Q. So this warp, we'll have like this chunk, this chunk, this chunk, this chunk, and we need all of them for our softmax output. So these intermediate results from each of the warps, and in between warps, we'll actually have to do synchronization, because these are like blocks of execution that we'll have to coordinate with each other. But if we do it this way in Flash Attention 2, then we're loading, basically these are all shared, and then doesn't and so for a given Q, when we are writing about a chunk of O over here, no more synchronization is required because we are sharing all of K, sharing all of V, and we can essentially compute it entirely independently across all the K blocks, V blocks, do our tiling and our accumulated or running calculations, and then write without any synchronization between warps. Is that a correct summarization?
Yeah. So I think the key thing to look at is it's better to have the loops on the outside with the Q, because you don't have to worry about racing on O anymore on the inner loop, right?
Mm-hmm.
Because if you're, you don't care actually about racing on K and V, because K and V never change, right? Everyone is reading from this. Everyone's doing reads. No one's doing writes. So you're not racing on those ever. So the key is that if you bring Q out to the outside loop, every chunk of Q is responsible for an independent chunk of O, right?
Yeah.
And then what you then you can parallelize that very easily, and you don't have to worry about any race on the inner loop, because the inner loop is read only, basically, right?
Mm-hmm.
So you don't care.
Yeah, I was kind of confused why they didn't do it this way in the first place, because these authors clearly have like a very deep understanding of both like the hardware as well as the like algorithmic side. And did they have in your understanding, did they have any reason for originally avoiding this particular this particular parallelization scheme in the first paper? Because surely they must have seen like we have to do all this like synchronization and like locking essentially when avoiding race conditions on our writes to the O accumulator block. Is there a reasoning for that, or did it just not occur to them as far as you're aware?
I think it was a mistake in the first. It's always easy in hindsight, right?
Yeah.
But they got 2 papers out of it, though. That's the real reason. Okay.
Okay.
You get 2 best papers this way.
Wow.
Yeah.
40 tests. Okay.
But yeah, no, it was an oversight. And it was actually interesting. I was listening to a presentation by Triton, who is the first author on I guess not the last flash attention, but most of them. And it was noted that he only started working with CUDA in like 2022. So he wasn't like a person who had 100 years of CUDA experience before he wrote his first paper. So it goes to show that you can make some things happen even if you don't have like perfect hardware understanding. And then you can actually see, as they've gotten from flash attention 1 to flash attention 2 to flash attention 3, the level of very, very in-depth, detailed hardware understanding has increased with each iteration, and that's one of the things that's made them a lot better.
Yeah, that's pretty awesome. I'm actually pretty interested in flash attention 3 now, with like TMA, and then isn't like WGMMA, isn't that like a specific like new instruction that's supported by the new hardware?
Yeah. So this is getting a little bit. I don't even program against H100s. So, but the TMA is asynchronous memory loading. So the idea is, actually, just the H100 thing in general is that they wanted to do more things asynchronously, where they don't want to be blocking to wait for memory. They don't want to be blocking to wait for tensor cores. So TMA, which is one of the instructions, is basically your CUDA cores are asking for a block of memory from shared memory, and then they can continue to do things while they wait for that block of memory to actually get there. And similarly, WGMMA, which is warp group matrix multiply accumulate, is a new instruction that was added for a whole warp group, which is basically a chunk of the whole SM, can launch a tensor core matmul, and then send that to the tensor core, and then continue to do stuff asynchronously, and then wait for the matmul result from the tensor core. and then you use that. So you can start to overlay things like activation computations and matrix multiply computations.
Interesting. So I thought kind of one of the value adds of GPUs is that it has like a warp scheduler which is aware of things and can like hide memory latency by like swapping out warps that are waiting on memory access and stuff. So with TMA specifically, is that just giving the programmer manual control of like when we do async memory loads and how we give control back to the hardware to like schedule things, or is it a little different than that?
Yeah, this is I don't know. Actually, you can definitely look. I was looking at the WGMA stuff a lot, so I know a little bit more about that. But yeah, I'm not actually super familiar with, because you are right that in theory you would think that you could do, zero overhead context switching. But I guess it could be that you want the same warp group to be able to continue on, which this is now speculative. I guess that's the disclosure, right? So you actually do want to keep executing the same thing. So you can basically say, I think I'm going to need this memory in a while, and then you can go back to computing activations on the exact same thread line, and then by the time it arrives, you're ready for this memory.
I see. That makes sense. So it's almost allowing it like within a specific warp group. It doesn't actually have to be. This
is speculation. I haven't looked at. I think that's what's happening, but this is getting a little bit. The H100 instruction set is a little bit past my knowledge level.
Well, that'll be homework for me, I guess. But that would make sense to me. And I see. Emily just pointed out that latency hiding with the warp scheduler, like I was talking about, requires having a lot of occupancy. So I guess one of the benefits of TMA is that you could have that latency hiding even with like low occupancy in your SMs, which I guess also makes sense.
Yeah. And I guess you don't have a lot of. I guess although if you have block parallelization, you have a decent number of separate thread blocks that are running at any point of time.
I see. So is there anything special about the backward pass we should go over? I actually haven't even, in both the paper and the code, I have not gone there yet because getting the forward pass working in Triton was a challenge. But is there anything special that's fun to talk about with that?
I think the thing that's very interesting about the backwards pass is actually fascinating, actually. And if you go to the first paper, I'd go to the first, this Flash 10 and 2.
Okay. Did I go past it? Okay, where are you? Let's go back up.
It's it's in the appendix. They didn't even care. Okay, they just threw it in the appendix. It looks very wonky because it's like all the details. Backwards pass, so it's the lower one, yeah. It's long.
Wow.
Yeah. So a few interesting notes here is this is one thing that when I was reviewing I hadn't even considered, is how do you do masking or for dropout in backwards, right? Because you normally have, say there's like a 10% chance that any one of these attention scores could have dropped out. How do you know if you don't even hold the O block, or not the O block, if you don't hold the attention score block, how do you know which ones you masked? And the mask is n by n, and you don't want to load that. So how do you do that, right? And the answer, which I didn't even realize what they were doing at first, is they're caching entropy. So they're caching pseudo-random state from the forward pass in order to regen exactly which values in the score matrix would have been masked.
That's hilarious. So wait, when you say caching, so they just have like the RNG state essentially, like and how big?
So they save the RNG state is tiny, right? Because you have you can always fit 32 bits is 32 bits of entropy, right? So that's 2 to the 32. You don't need more than that. So it's probably just one thing that you're rolling and regenerating numbers on. So it's a scalar way of caching your quadratic mask.
So essentially,
which I thought was very clever.
Is the seed what you're referring to? Just like
the seed is small, and then just every time you have to say, well, you're just regenerating the mask by saying this is how it would have been during the forward pass. And you can see that. I'm trying to see which line that is. Is it
This?
18?
Oh,
Oh, is that the?
P dropped.
Oh no, it might be 15. I'm trying to remember which one. Which one is a dropout mask? Yeah, dropout mask is. So they compute it. They sort of regenerate it on line 14, and then they put it. They re-pointwise multiply it in on line 15, which I thought was pretty funny.
That is funny. So they're just recomputing it. So it's like a weird RNG version of activation checkpointing, sort of, where they're just recomputing on the backward pass rather than storing this giant quadratically sized chunk of memory. That's really interesting.
I thought that was a very clever technique. But the other thing is that's sort of interesting is in the backwards pass, you need to save a few things from the forward pass because you don't have these. You're missing these normal products that you would have. You're missing the matrix before it's been scored and stuff, and you're missing the score matrix before and after softmax, right? So you need to both regenerate those, but then you need to use cached L values, these cached denominator values, and these cached max values from your forward pass to compute the backwards pass.
That makes sense. Do we know how? Because I'm just thinking about this. In a given thread block, which will be running on a specific SM, and that will have a specific like block of shared memory, we cache, say, one denominator we calculate in the forward pass, one max we calculate in the forward pass per element or per query vector, basically per if we have like block size Q, we'll have block size Q statistics, right? We cache those, but then during the backward pass, how do we ensure that the backward pass kernel is actually executed on that same SM, so those cached values, or do we have to store those in HBM?
No, you're gonna get them saved in HBM, and then the kernel is gonna return a pointer to them, right? Or you're gonna save them in a certain spot and then you can, in the backwards pass, say, oh, this is where I've cached these in HBM when you're launching the kernel, right? You're gonna pass that as a pointer.
Got it. Interesting. Well, this will be a fun one to implement. It looks more complicated.
I think the backwards pass is actually a little bit nastier than the forwards pass.
Yeah.
Especially if you're trying to support things like dropout and all the sort of fancier features. Although you don't have to support dropout.
Well, this is really cool. I've learned so much through. I'm glad we chose this as our second session. It was a jump up in complexity, but this has been on my list to do a deep dive on for a while. So this is awesome. Any other quick hold on, where's that slide? Any other topics that are? Oh, we just did talk about them actually. What needs to be saved for the backward pass, and then caching the RNG state, dropout. Cool. Any other topics? That was all I had. Does anybody else have any other topics? All right. If there's no other topics, do you have anything else, Ben?
No, I think that covered it.
Sweet. Well, thanks again for putting together the slides and kind of building incrementally from the problem to kind of intuitive solutions that end up not working, and then finally to our final solution that kind of helps build the intuition for how this works and why it's implemented the way it is. So yeah, I really appreciate you volunteering for session 2. I guess next we should maybe do another quick poll in the Discord this weekend to figure out what our next topic will be, maybe in like 2 weeks from now, if that sounds good to everybody. And yeah. Awesome.
Thanks for coming out, everyone.
Yeah. All right, I'll stop the recording.